Welcome to section 4.11. This is the 46th session of the ISACA CISA exam prep series. In this session, we'll cover database management. We'll answer several questions. What does a database management system actually do? How is it structured underneath? What are the main database models? How does the relational model keep data clean? What controls keep a database safe? And what does an auditor review when checking one? Why does this matter beyond the exam? Because the database is where your organization's truth lives. Picture an airline's booking records or a clinic's patient histories. If that data is wrong, duplicated, or exposed, the damage is real. A database management system is the gatekeeper for all of it. Understanding it lets you judge whether the crown jewels are protected. Get this right, and your data is consistent and secure. Get it wrong, and the whole business inherits the mess. So what does a database management system actually do? Think of it as a librarian for your data. It helps organize, control, and use the data that applications need. Its core jobs are clear. It reduces duplicate data, it cuts the time needed to reach data, and it provides basic security over sensitive information. The data sits in multiple levels. The smallest piece is a field, like a customer identifier. How does the system know what its data means? Through a data dictionary. It records each field along with its characteristics and uses. There are two flavors. An active dictionary takes part in processing. It can enforce validation rules or print formats automatically. A passive dictionary is just a reference you can view or print. Think of an active one as a spell checker that actually corrects you. A passive one is just the dictionary on the shelf. How tightly can you control who reaches the data? Very tightly, at many levels. You can control access between a user and the database, between a program and the database, between a transaction and the database, between a program and a single data field, between a user and a transaction, and between a user and a single field. So you can be as broad or as surgical as the risk demands. Why bother with a database management system at all? The advantages stack up quickly. Applications gain data independence. Changing requirements are easier to support. Transaction processing is efficient. Redundancy drops and consistency rises. Shared data lowers maintenance cost. You can enforce data and programming standards. You can enforce security and run integrity checks. And users can query data ad hoc through a query language. How is the system structured underneath? It rests on metadata, which is data that defines data. Metadata describes fields, files, relationships, and queries. It lives in three schemas. The conceptual schema is the overall logical view. The external schema is each user's tailored view. The internal schema is how data physically sits on disk. If those three do not mesh, the system fails its users. Each level uses a data definition language to build its blueprint. The conceptual level maps the external views to the internal storage. So users never need to know the physical layout. What manages all that metadata? A data dictionary and directory system. The dictionary indexes and describes every item in the database. A directory tracks where each piece of data lives and how to find it. It lets the administrator create and modify definitions safely. It validates those definitions to protect integrity. It blocks unauthorized changes to the metadata. And it answers queries about the data definitions. One system can serve several databases. That eases switching from one product to another. The payoffs include better documentation and standardized methods. What are the main database models? There are four classic structures: hierarchical, network, relational, and object-oriented. Start with the hierarchical model. It arranges data as parents and children, like a family tree. Each child has exactly one parent. So expressing multiple parents forces you to duplicate data. It is easy to build and search when relationships are truly tree-shaped. The Windows registry is a familiar example. Next is the network model. Its building block is called a set, with owners and members. A record can belong to more than one owner. That flexibility makes these structures complex and hard to repair. It is rarely used today. And both these older models cannot handle high-level queries. The program itself must navigate the data. What makes the relational model so popular? It organizes data into simple tables. A table has rows and columns. Rows are records and columns are fields. Most enterprise systems run on relational databases. The tables follow strict properties. Each value is a single, indivisible unit. Each row carries its own unique identity. Column values are all of the same kind. And the order of rows and columns does not matter. You designate some fields as keys for fast searching. A join then links related records across tables by matching values. Relationships are defined only at retrieval time, so the model is dynamic. It is also independent of the physical storage. That makes it far easier to understand, modify, and secure. How does the relational model keep data clean? Through normalization rules. The goal is to store the minimum needed to answer queries. Each attribute holds just one value for a given record. Attributes are elementary, with no hidden internal structure. Every record has a primary key that identifies it. The other attributes depend fully on that key. And a foreign key must either be empty or point to a real row elsewhere. That last rule is referential integrity. Think of it as forbidding a link to a page that does not exist. What about object-oriented and modern databases? An object-oriented system stores information as objects, not flat data. That brings encapsulation and inheritance from programming. So objects carry both code and data together. Each object gets a unique identifier and loads quickly when referenced. It shines for engineering, science, graphics, and sound. Those things are hard to fit into neat relational tables. Then there is the not only structured query language family. It rose to handle the flood of big data on the internet. Much of that data is unstructured, like video, posts, and logs. Those records will not break neatly into relational components. This family comes in several models. Key value stores pair a name with a value. Column-oriented stores group all values of a column together. Graph databases model relationships between objects. Document stores hold structured documents. Time series stores stamp every data point with a time. And spatial stores handle maps and coordinates. Two advantages stand out. Sharding spreads data across servers to share the load. And dynamic schemas let you add data without defining structure first. What controls keep a database safe? Several work together to guard integrity and availability. Enforce definition standards. Backup and rehearse recovery so the database stays available. Set access controls, including privileged access down to the table and field. Restrict updates to authorized people only. Handle concurrency so two users cannot corrupt the same record. Build accuracy and consistency rules into the table definitions themselves. That way, no programming flaw can bypass them. Use checkpoints to limit data loss after a failure. Reorganize to reclaim space and verify relationships. Follow restructuring procedures for logical and physical changes. Monitor efficiency with performance reporting tools. Block non-system utilities that could bypass security. And consider database activity monitoring to watch and report on access. What does an auditor review in a database? You look across several areas. Check the logical schema, so entities and relationships are properly defined. Check the physical schema, so storage and indexes match the requirements. Review access time reports to confirm indexes minimize delays. Examine security controls, like roles, passwords, and encryption. Confirm production data copies are authorized and masked when sensitive. Review interfaces with other programs for integrity during import and export. Check backup and disaster recovery procedures for availability. Review the broader controls the database supports. And confirm asset management basics, like an owner and a valid license. In short, you ask whether the design protects the data it holds. So let's bring it together. A database management system organizes, controls, and protects data. Underneath sit 3 schemas and a dictionary that defines everything. 4 classic models exist, with relational dominating most systems. Normalization and referential integrity keep relational data clean. Object-oriented and not only structured query language models cover the rest. Layered controls guard integrity, availability, and access. And an auditor reviews design, access, recovery, and ownership. Master this, and you can judge whether the data can be trusted. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.